one thing you can count on in every equation, in every formula, is that the left side is equal to the right side. That's the whole point of the equal sign. So what if we had an unequal sign instead? What's the point of that? Well, let's find out. We're going to use two different kinds of not equal signs. The first one means is bigger than, and we use it to say, for example, that x is bigger than y, or something obvious like 3 is bigger than 2. You can guess that the other sign points the opposite direction and has the opposite meaning. We use it to say, for example, that a is smaller than b, or that 5 is smaller than 7. All of these expressions are called inequalities, and that's what this module is about. If you can't remember which side should be smaller, notice that the small end of each sign points at the smaller number. Notice also that even though the two signs have opposite meanings, we can make an inequality say exactly the same thing using either of them. How? By changing where we write which number. These two expressions both tell us the relative size of 6 and 8. When we try to work with expressions that are inequalities, it helps to use the number line you saw working with signed numbers. The line reminds us that negative numbers step to the left of 0, positive numbers step to the right. A number that is smaller or less than another number will always be on its left. A number that is bigger or greater than another number will be on its right. 2 is less than 3, for example. Which side of 3 is it on? The left. In exactly the same way, negative 4 is less than negative 2. Negative 4 is to the left of negative 2. Let's look at the other way we can write an inequality. This example says positive 2 is bigger than negative 2, and that's correct. It's to the right of negative 2 on the number line. What if we use a variable? What do we mean when we write the inequality x is bigger than 3? We mean x can be any number larger than 3, which means any number to the right of 3. We need a way to show that x is greater than 3 does not include the number 3 itself. We show that on our number line by making an open circle at 3 to mean not including 3 itself. If we wanted to include 3 to say 3 or larger, we would have to change the open circle to a closed circle, a big solid dot. That would mean equal to or larger than 3. We need a new symbol to express that relationship. And here it is. X is equal to or bigger than 3. As you might guess, there's an opposite sign meaning is equal to or less than. It points in the opposite direction. Okay, that's clear enough, but what do we do with an expression that looks like this? How would you read it? Each part is simple enough. 2 is less than or equal to x. X is less than or equal to 3. When we have a variable, our first question usually is, what is its value? How big or little can it be? So we turn the first expression around to get the x on the left and say, x is equal to or greater than 2. The second expression is already the way we want it. X is less than or equal to 3. And that tells us that x can be equal to 2 or equal to 3 or anything in between. We'll use pictures and notation like these to show answers to inequality problems. Yes, there can be inequality problems. We do solve inequalities. But what does it mean to solve x plus 2 is less than 5? It means find all values for x such that adding 2 gives an answer less than 5. You can think of some values for x right away. 0 and 1 will work. But we need a way to find all the values of x. And in fact, you know it already. The steps we use to solve an equation like this, x plus 2 is equal to 5, is exactly the way we'll solve our inequality. X plus 2 is less than 5. Let's try it. To solve the equation, we have to get x off by itself. How? In this case, we subtract 2 from both sides, leaving us with x equals 5 minus 2, or x equals 3. When we solve the inequality, there will be one difference. The expression doesn't have an equal sign. It has an inequality sign. That's it. Aside from that, no difference. None. Nada. We get the x by itself by subtracting 2 from both sides. Which leaves 3 on the right, giving us the answer x is less than 3. This means that any number smaller than 3 will make our inequality true. And we graph it this way on our number line with the circle at 3 open to show that 3 is not included, only numbers less than 3. That's good news, but it's never quite that simple, is it? We can handle inequalities just like equations as long as we're adding or subtracting. Bad news is multiplying and dividing gets a little tricky. We'll deal with that in a moment. First, give this one a try. It shouldn't be tricky. Solve the inequality by treating it just like an equation. Pause the program until you have it solved, and then click the play button, and we'll compare our steps. Since we can treat this just like an equation, I'll pretend it is. And this equation can be solved in no time by subtracting 1 from both sides to gather the numbers, and subtracting 2x from both sides to gather the x's. What does x equal? -8. Now if I back up and put the inequality sign in place of the equal sign, the one that says is equal to or greater than, I'd use exactly the same steps to get the answer. What is x equal to or greater than? -8. And the solution looks like this when I graph it on the number line. If you had trouble working out the steps to our solution, be sure to review the modules on linear equations and brush up on the tricks we learned there, because they're exactly the same ones we just used here. That's true whenever we add or subtract. But what if we're solving an inequality and we have to multiply or divide? Well, to be able to do that, you have to keep straight some things about positive and negative numbers. Quick, is -2 to the left or to the right of -3? Question 2, is +2 to the left or to the right of +3? Did you get it right? Good. You noticed immediately that -2 is to the right of -3. It's bigger than -3. But on the positive side of 0, it's just the opposite. 2 is to the left of 3. It's smaller than 3. In other words, on the left side of 0, counting negatively, -1, -2, -3, 4, your values are getting smaller. On the right side, positive 1, 2, 3, 4, the values get bigger. Now here's a big question. Do we ever cause a number to jump instantly to the other side of 0? Yes, we do. Every time we multiply or divide by a negative number. Take this inequality, for example. 2 is less than 3. Multiply both sides by -1, and the whole thing jumps to the other side of 0 on our number line, where -2 is greater than -3. The inequality sign turns around. The less than has become greater than. This happens every time we multiply or divide both sides by a negative number. We jump to the other side of 0, and no matter which way the inequality sign is pointing, greater than or less than, we have to turn it around. Notice that multiplying by a positive number is much simpler. We don't jump to the other side of 0, so we don't have to change the sign. You can see it in this example, where we multiply both sides of the inequality, 2 is less than 4, by 3. Giving the correct result that 6 is less than 12. We don't have to change the inequality sign at all, just as we saw earlier with addition and subtraction. We're not jumping to the other side. In those cases, we're just sliding both numbers an equal distance along the axis. In this example, plus 3 steps. Let's try a problem that puts all of this into practice. We just happen to have one handy. First, we're going to multiply out the brackets or parentheses. As always, we're careful about multiplying two negatives. and then combine like terms on the right. And then what? Move the 22x by subtraction and combine like terms on the left. Gather the numbers over to the right side by adding 3 to each side. Collect terms again, and then change the negative 10x to a simple x by dividing both sides by negative 10. Negative 10? Warning bells, warning bells. Remember our number line. We are dividing both sides by a negative number. That means we're jumping to the other side of 0. So we have to turn the inequality sign around, finally reaching our answer. X is greater than 6 over 5. We can think of that as 6/5 or 1 1/5, all the same thing when we graph it onto our number line. Notice that everything we did was exactly the same as for equations, except when we divided by negative 10. Where do we use inequalities? They're good in lots of cases where you have some sort of upper or lower limit, but you don't have enough information to write an equation. Have you ever been in a situation like this one? Now let's see how you do with this problem on your own. I'll give you one hint. Begin by multiplying to remove the fractions. Pause the program while you find your answer. When you're ready, click play and we'll compare steps. This one looks hard, but one step at a time gets the job done, right? Here's how I worked it out. First, those fractions. We need the lowest common denominator of 3 and 5, which is 15. We multiplied both sides by 15. Multiplying by a positive number does not change the inequality. Canceling the denominators gets rid of all the fractions. We are definitely making progress here. Then we multiply out the brackets and collect the like terms. Add 6 to both sides. And add 60y. And last of all, we divide both sides by 59, which doesn't change the inequality because it's positive. Now we draw the graph. We can leave the answers this way, or we can write it as a mixed number, 3 and 9/59. Is that what you got? If not, you can review this lesson to see where you got off track. In either case, you should practice on examples in your book until even problems like this become easy. And don't worry, they will.